Lecture for Chapter 15, where we discuss acids and bases as part of our section on equilibria. Now, this is our first video lecture, and we'll be discussing how to define acids and bases and some of the basic concepts related to acids and bases. Now, before we start defining acids and bases, you're probably familiar with the concept of acids and bases at a basic level. And there's lots of applications to your daily life related to acids and bases. I first want to look at stomach acid and how it relates to heartburn. The cells that line your stomach produce hydrochloric acid, or HCl. And that's actually very beneficial because it helps to kill unwanted bacteria. It also helps to break down food, and it also activates enzymes that break down the food in addition to the acid itself breaking down the food. Now, if that stomach acid backs up into your esophagus, it irritates those tissues, resulting in heartburn. This is also known as acid reflux, or GERD, so gastroesophageal reflux disease, which is chronic leaking of stomach acid into the esophagus. Now, mild cases of heartburn can be cured by neutralizing the acid in the esophagus. And this can be done simply by swallowing some saliva, because that actually contains a bicarbonate ion, or by taking an antacid that contains hydroxide ions and or carbonate ions. Now, the properties of acids. If you think about a lemon, and a lemon is very acidic, it has a sour taste associated with it. Acids react with active metals. Examples of active metals include aluminum, zinc, iron, but that does not include copper, silver, or gold. For instance, aluminum will react with hydrochloric acid to produce aluminum trichloride and hydrogen gas. This is why you never want to bake pineapple upside down cake in your aluminum baking pan, because it'll actually react. The acid in the pineapples will actually react with the pan and cause some nastiness. So you always want to bake something like a pineapple upside down cake or anything acidic in a glass pan. The acids also react with carbonates, and it produces carbon dioxide gas. So carbonate examples include marble, baking soda, chalk, or limestone. Here's an example of the chemical reaction that takes place. So calcium carbonate plus 2 equivalents of hydrochloric acid form calcium chloride, carbon dioxide gas, and water. So this is the famous volcano reaction that you see so many students doing, where they react baking soda with vinegar to liberate carbon dioxide. Acids also change the color of vegetable dyes. This is because they contain chemicals called phytocyanins. For example, acids turn blue litmus red. And those acids also react with bases to form ionic salt. So acids plus base will neutralize each other. And in the process, they'll form an ionic salt. So this is where you have to remember some of those neutralization reactions that you learned from Chem 1A. Here are the names of some common acids that you should be familiar with, and you should already know how to name. Nitric acid, sulfuric acid, hydrochloric acid, phosphoric, acetic, hydrofluoric acid, carbonic acid, and boric acid. So these common acids have a lot of different uses in everyday life. Carbonic acid is also in your soda when you drink a carbonated beverage. HF is used in some industrial strength glass cleaners, but you have to be very careful because it's very reactive. It actually eats the glass. Boric acid is actually used to kill roaches and other insects. It works by dehydrating the insect and actually killing them. Now, there are a couple of videos embedded into the PowerPoint, but you also have access to these videos made by the publisher on Blackboard. So if you'll please watch those through the link in Blackboard. So let's talk about these structures of acids. Binary acids have acidic hydrogens attached to a nonmetal atom. For example, HCl or HF. Oxyacids have acidic hydrogens attached to an oxygen atom. For example, sulfuric acid or nitric acid. So notice in this structure here of the sulfuric acid, when we draw the Lewis dot structure, it's missing some of the lone pairs, but you have these OH groups here. And these OH groups here, these hydrogens are actually very acidic, meaning that the protons will dissociate from the oxygen. So they'll dissociate as So they'll dissociate as H plus, and they'll leave that oxygen behind as a negative. So that's still attached to the, so I'm not going to show it breaking up. So hydrogen will dissociate to form an H plus. And the same thing with the nitric acid. So you have another proton here that will dissociate as H plus and leave behind the NO3 minus. Now later on in these slides we'll discuss why those protons are acidic and why they will leave the molecule when we discuss more about oxyacids. So more about the structures of acids. Here we show two different acids. We've got citric acid on the left, malic acid on the right. These are both examples of acids that have carboxylic acid groups. So the carboxylic acid group is that COOH. So if we're looking at that there's that carboxylic acid group in the citric acid, and there's that carboxylic acid group in the malic acid. And it's that hydrogen on that OH that is actually acidic, so it will dissociate to form the H plus. Now when we look at the chemical formulas written here to the left, where we've got the acetic acid and the citric acid, when they write the hydrogens out in front, instead of carbon, hydrogen, and oxygen, one of the hydrogens is written in front. This is telling you that you have one acidic hydrogen in that compound. So in citric acid, notice that there are 3 hydrogens written out in front. This is telling us that there are 3 acidic protons in the citric acid. Notice there's a proton there that can dissociate, one that can protonate there, and then the one in this carboxylic acid group. Notice that this hydrogen, this OH, is not acidic. This one's not acidic because it's not part of a COOH. It does not have it's not part of a carboxylic acid group. So only the first hydrogen in the formula is acidic. And that's the proton in the COOH. And remember, this is the carboxylic acid group. So that's the acidic proton. Now let's contrast the properties of acids to bases. Now the bases are also known as alkalis. So that's where in the periodic table we talk about the alkali metals and the alkaline earth metals. Those are ones that form bases. Now the bases taste bitter. Plants contain alkaloids and they're often very poisonous. But those alkaloids are what give them their bitter taste. And then the solutions of bases actually feel slippery. And the bases will change the color of vegetable dyes, but in a different manner than the acids did. So the red litmus actually turns blue in the presence of a base. And again, bases will react with acids to form ionic salts, and this is a neutralization reaction. Some common bases are sodium hydroxide, potassium hydroxide, calcium hydroxide. Notice that these are all hydroxides. And a common use for these hydroxides you may be aware of is in drain openers and drain cleaners. Other bases include sodium bicarbonate, which is baking soda. It's also used in cooking and as an antacid ingredient. Magnesium hydroxide is one of the active ingredients in milk of magnesia, an antacid. And ammonium hydroxide, which is used in fertilizers and some detergents. Again, there's another video to introduce you to aqueous bases. I recommend that you watch that through the link in Blackboard. Now, most ionic bases contain OH ions, for example, the sodium hydroxide or calcium hydroxide. Some of those bases also contain carbonate ions, so that's a CO3 with a 2- charge, for example, calcium carbonate or sodium bicarbonate. Molecular bases contain structures that react with protons. These are mostly amine groups. Now, indicators are chemicals which change color depending on the acidity or basicity of the mixture. So indicators indicate the acidity or pH or the basicity of the mixture or the solution. Many vegetable dyes are indicators because they contain anthocyanins. For example, purple cabbage is a really great example. or also if you have any hydrangeas in your yard. They'll change color based on the pH of the soil. Litmus is another example of a natural indicator. It's derived from Spanish moss, and it turns red in the presence of an acid and blue in the presence of a base. Another type of indicator is phenolphthalein. Phenolphthalein is a common indicator that we actually use in the lab. It's also formerly found in laxatives, and it turns a nice hot pink color in the presence of a base, but in the presence of an acid, it's actually colorless. So we're going to first talk about acids and bases in terms of Arrhenius theory. And bases dissociate in water to produce hydroxide ions, so OH minus ions and cations. And these are ionic substances that dissociate in water, such as sodium hydroxide. So this is an example of an Arrhenius base, so it produces an OH ion that dissociates in water. Acids ionize in water to produce H plus ions and anions. So Arrhenius theory says that there has to be a proton that can dissociate. Because molecular acids are not made of ions, they cannot dissociate. They must be pulled apart or ionized by the water. For example, we're looking at HCl. The HCl dissociates or gets pulled apart by water to make H plus and Cl minus. Remember that the ionizable hydrogen is written in the front. So in the case of acetic acid here, the proton's written in front, and that shows you that when it dissociates, it produces the H plus and the acetate ion. The protons produced by the acid are so reactive that they cannot exist in water. And remember, the H plus ions are termed protons. Instead, they react with water molecules to produce complex ions, mainly the hydronium ion, which is the H3O plus. So remember that those H pluses are so reactive, they're not going to just exist on their own in solution. They're going to grab a water, and that's why we write the hydronium ion. This is an example of that proton adding to the water molecules to form the hydronium ion. Now in reality, many more waters associate with the proton, but for simplicity's sake, we only show one of those waters binding to the protons. In Arrhenius acid-base reactions, the proton from the acid combines with the hydroxide from the base to make a molecule of water. So this is the neutralization part. It's often helpful to think of water as HOH. The cation from the base combines with the anion from the acid to make a salt. So an acid plus a base makes salt and water. Here we have the example of HCl, hydrochloric acid, combining with sodium hydroxide, the base, to make sodium chloride salt and liquid water. Now, there are some problems with Arrhenius theory. It doesn't explain why molecular substances like ammonia dissolve in water to form basic solutions, even though they don't contain OH ions themselves. Nor does it explain how ionic compounds like sodium carbonate or sodium oxide dissolve in water to form basic solutions, even though they don't contain OH ions. It also doesn't explain why molecular substances like carbon dioxide dissolve in water to form acidic solutions, even though they don't contain proton ions themselves. It also doesn't explain acid-base reactions that take place outside of aqueous solutions. So remember, with Arrhenius theory, it had to be in water. So this is where the Brønsted-Lowry theory helps. So in the Brønsted-Lowry acid-base reaction, an H plus is transferred, so the proton is transferred. This takes care of some of the problems we had with the Arrhenius theory explanation of acids. The Brønsted-Lowry theory, the reaction doesn't have to take place in aqueous solution, so it has a broader definition than the Arrhenius theory. The acid is the proton donor, and the base is the proton acceptor in Brønsted-Lowry theory. The base structure must contain an atom with an unshared pair of electrons to be a proton acceptor. In an acid-base reaction, the acid molecule gives a proton to the base molecule. So here in this generic reaction, we have this acid with the proton bound to it, so we're represented as HA. and the presence of a base, the base we've put a lone pair on that base, the proton gets transferred. So as the HA loses the H+, it leaves behind its electrons, so the A now has a negative charge and it's got a lone pair left on it. And now the base is protonated with the H+. When you add an H+ to the B that's neutral, the base that's neutral, it is now has an overall positive charge, so it's Hb+. The Brønsted-Lowry acids are proton donors. Any material that has a hydrogen can potentially be a Brønsted-Lowry acid. Because of the molecular structure, often one hydrogen in the molecule is easier to transfer than others. So you'll be discussing this a lot more when you get into organic chemistry. So we're laying down a very good foundation of information about what you need to know about acid-base theory here in Chem 1B, but this is also the groundwork for what you need in your upper division chemistry courses such as organic or biochemistry. Now, hydrochloric acid is acidic because the HCl transfers a proton to water, forming the hydronium ions. The water acts as a base and accepts the proton. So let's look at that. So the HCl, which is our acid, and we have H2O, which is our water, which is acting as a base. The proton dissociates from the chloride. That proton then protonates our base to form the hydronium ion, the H3O+, which leaves behind the Cl- from our acid. So we have the transfer of the proton in the acid-base reaction with the Brønsted-Lowry definition. Now remember, with the Brønsted-Lowry definition of bases, the bases are the proton acceptors. Any material that has atoms with lone pairs can potentially be a Brønsted-Lowry base. Because of the molecular structure, often one atom in the molecule is more willing to accept proton transfer than others. Let's look at ammonia. Ammonia is basic because NH3 accepts a proton from water, forming hydroxide ions. So the water acts as an acid because it's donating protons. This is also too where you need to remember how to draw your Lewis-Dot structures. If we look at the Lewis-Dot structure of NH3, remember it is a trigonal pyramidal complex and it has a lone pair. So its electronic geometry is tetrahedral, but the molecular geometry is trigonal pyramidal. So when the ammonia is dissolved in the water will act as an acid and will give up one of its protons, and it will protonate one of the lone pairs. So the water will lose an H+, it'll add to the lone pair at the base to form the NH4+, and when the water loses its proton, it leaves behind a hydroxide ion. So notice we have a balanced chemical equation, and also the charges are balanced. Now you probably noticed in our examples with the acids and bases that in one case the water was the base, and then the other example, water was the acid. Water is what is termed as an amphoteric substance, meaning that it can act as either an acid or a base. So remember that ampho is kind of that ambivalent nature. It can act as one or the other or two, kind of like amphibians live in both the water and land. Amphoteric means that it can act as an acid or a base. So they have both a transferable proton and an atom with a lone pair. Water acts as a base accepting protons from HCl, as from our previous example, and water acts as an acid donating a proton to ammonia, as in the other example that we looked at. Now, one of the advantages of Brønsted-Lowry theory is that it allows reactions to be reversible. Notice here that we all have that reversible arrow sign. So this means that we have an equilibrium. The original base has an extra proton after the reaction, so it will act as an acid in the reverse process. And the original acid has a lone pair of electrons after the reaction, so it will act as a base in the reverse process. So if we're looking at that in here, this is our acid and this is our base. If we write this reaction in reverse, what was our A is now a base, because the base can accept the proton and it can reform its acidic form of the HA. So it's indicating that reversible nature of the reaction, and this introduces us to the concept of conjugate acid-base pairs. In a Brønsted-Lowry acid-base reaction, the original base becomes an acid in the reverse reaction, and the original acid becomes a base in the reverse process. Each reactant and the product it becomes is called a conjugate pair. So in our example here with ammonia reacting with water, water and hydroxide are a conjugate pair. And the ammonia and the ammonium make a conjugate pair. The original base becomes a conjugate acid, and the original acid becomes the conjugate base. So in our example, water is our acid and it's related to its conjugate base, the hydroxide. And vice versa, the ammonia, which is our base, becomes its conjugate acid, the ammonium. So the ammonia is the base and becomes the ammonium conjugate acid. So these are just some examples to help you better understand some of those acid-base reactions, where we have the generic equation HA representing the acid and our base with the lone pair. So the acid gives up its proton, protonates the base to form the conjugate base, the A-, and the protonated base becomes the conjugate acid. This example here, where we have the acid protonates the base, so we have the formic acid protonates the water, which is our base, to form the formate ion, and creates our conjugate acid, the H3O+. Whereas if we have ammonia reacting with the water is acting as the acid, and it protonates the ammonia to form the ammonium conjugate acid, and the hydroxide is the conjugate base of the water acid that's acting as the acid. So here's a little practice. You may want to pause the video and see if you can write out the conjugate acid of the following. So if we are writing the conjugate acid of the water, we're simply adding an H+. So the formula would be H3O+. For the ammonia, it would be ammonium, so NH4+. For the carbonate, it would be bicarbonate, so HCO3-. And for the H2PO4-, it would be the phosphoric acid, so the H3PO4. Notice that each time that we created the conjugate acid, we just added an H+. Now let's write the conjugate base from the same set of molecules. So remember, the conjugate base, we need to remove an H+. So if we're looking at water, we would form hydroxide when we remove the H+ or the proton. If we removed a proton from ammonia, it'd form NH2-. Now notice with the CO3 2-, there are no protons to remove. So since it does not have any protons or hydrogens, it cannot act as an acid. And if we're removing a proton from the H2PO4, this would make HPO4 2-. So make sure you balance out those charges on the molecules. Let's just make sure we discuss some arrow conventions. Chemists commonly use two kinds of arrows in reactions to indicate the degree of completion of the reaction. A single arrow indicates all the reactant molecules are converted to product molecules at the end. A double arrow indicates that the reaction stops when only some of the reactant molecules have been converted into products. So remember, we use these double-ended arrows for equilibria reactions. Now again, in these notes I've got the funny little double-ended arrows like this because PowerPoint has this already built in. It does not have this built in PowerPoint, and it's a little bit more difficult to draw, so I'm just using this as a shortcut to represent these double-ended arrows. Now let's discuss what it means to be either a strong or weak acid or a strong or weak base. A strong acid is a strong electrolyte. And if you'll remember from your Chem 1A course, a strong electrolyte is a molecule that completely dissociates in water. So practically all the acid molecules ionize. So it's a one-way reaction, so we show just a one arrow going in one direction. A strong base is a strong electrolyte. So practically all the base molecules form OH ions either through dissociation or reaction with water. And again, this is a one-way reaction, so we only show the one arrow. But a weak acid is a weak electrolyte. And remember from Chem 1A, a weak electrolyte only partially dissociates. So only a small percentage of the molecule is ionized. And this is where we have to use the double-ended arrows to indicate that it forms an equilibrium. And just like a weak acid only partially dissociates, a weak base only partially dissociates. A weak base is a weak electrolyte. Only a small percentage of the base molecules form OH ions, either through dissociation or reaction with water. And again, because only a small percentage dissociates, it's an equilibrium, we use the double-ended arrows to indicate that it is an equilibrium and that it's a reversible reaction. So going back to the strong acids, the stronger the acid, the more willing it is to give up its proton. And we'll use water as the standard base. So here we have HCl dissolved in water. Strong acids donate practically all of their hydrogen ions. So it donates all of their H pluses, their protons. 100% is ionized in water because it's a strong electrolyte, it completely breaks up. So the concentration of the hydronium ions, the H plus ions, is going to be equal to the concentration of the strong acid because it completely dissociates. So if we put in 1 molar HCl, all of that breaks up into form 1 molar H plus and 1 molar Cl minus. But the weak acids donate a small fraction of their protons. Most of the weak acid molecules do not donate protons to water. Much less than 1% is ionized in water. So if we're looking at HF, HF is a weak acid and it only partially dissociates. So notice in the picture here that HF, most of the HF molecules are still bound to each other, so it's still one unit. Only a few have broken up to form the F minus and the H3O hydronium ion. Now because it only partially dissociates, the concentration of the protons is much, much smaller than the concentration of the weak acid. Often acid molecules have more than one ionizable proton, and the ones that have more than one ionizable proton are called polyprotic acids. The ionizable protons may have different acid strengths or be equal. If a molecule has only one proton that's ionizable, it's a monoprotic acid. If it has 2, we call it a diprotic. If it has 3, a triprotic. So we use those prefixes to let us know how many acidic protons are in the molecule. So for example, hydrochloric acid is a monoprotic acid. Sulfuric acid is a diprotic acid. Notice you got the 2 hydrogens out in front. And phosphoric acid is a triprotic acid. Polyprotic acids ionize in steps. So each ionizable proton is removed sequentially, so one at a time. So removal of the first proton automatically makes the removal of the second proton harder. So if we're looking at sulfuric acid, the H2SO4, sulfuric acid is a stronger acid than the HSO4 minus. And you can rationalize this based on the charge. So if the sulfuric acid is neutral and you remove a positively charged, it leaves behind the HSO4 minus. Now the HSO4 minus already has a negative charge, and most things want to stay neutral. So if I remove an extra proton, I'm removing an H plus. So if I remove an H plus from the HSO4, that creates SO4 2 minus. So it's going to be even more difficult to remove a positive charged proton from the HSO4 because it already has a minus charge, whereas the H2SO4 is neutral. So taking off the second proton is always more difficult than taking off the first. Now on the cover sheets for your exams, you'll be given a list of acids and bases. And here they're ranked in increasing acidity, where at the top here we have perchloric acid and sulfuric acid. So these are the most acidic of the acids, whereas OH minus, the hydroxide here, OH minus, the hydroxide, is the weakest of the acids. Now in the next column you have the conjugate base. So remember, the conjugate base is where the acid has had one of the protons removed. So the HClO4 becomes the ClO4 minus. And notice that at the top of this column are the weakest of the bases. And increasing basicity goes as you go down the column. So what you should notice is that the strongest acids make the weakest conjugate bases. So the strongest acids make the weakest conjugate bases. And conversely, the weakest acids produce the strongest conjugate bases. So there's an inverse relationship to the strength of the acid and the strength of the conjugate base. Commonly, acid or base strength is measured by determining the equilibrium constant of a substance reaction with water. For example, if we're looking at an acid forming in water, the further the equilibrium position lies to the products, the stronger the acid or base. The position of equilibrium depends on the strength of attraction between the base form and the proton. Stronger attraction means stronger base or weaker acid. So remember, in the strong acid, you have weak attraction, so you get complete ionization because they completely break up. Whereas in a weak acid, you have some strong attraction between the proton and the anion that's formed, so you have only partial ionization, so only part of them break up because of the stronger attraction in the weak acid compared to the strong acid. So more about the general trends in acidity. The stronger an acid is at donating protons, weaker the conjugate base is at accepting the proton. Also too, the higher the oxidation number, the stronger the oxyacid. So if we're looking at sulfuric acid, let's determine the oxidation state within the sulfuric acid, the sulfur. This oxidation state of the sulfur is +6 in the sulfuric acid, and in the sulfurous acid, the sulfur oxidation state is +4. Now hopefully you remember how to determine the oxidation states. So if we want to do this, let's do this real quickly. For example, which are +1, we don't know the oxidation state of the sulfur, that's what we're trying to determine. And there are 4 oxygens, and each one has a -2 charge, and the overall charge of the complex is 0. So if I solve the algebra, the 2 plus the -8, so the sulfur has to be a +6 oxidation state. And if you need practice in determining the oxidation numbers, you can try with the other molecules shown here. In our other example, where we've got nitric acid and nitrous acid, the nitrogen has an oxidation state of +5, and the nitrogen in the nitrous acid has an oxidation state of +3. So the higher the oxidation state of that central atom, the stronger the oxyacid is. So you can think of, the difference in electronegativity too. That central atom is pulling electron density. It has a very high positive charge, so it's going to want to pull electron density towards it, and as it pulls electron density towards it, it causes the proton to be more acidic. So the higher the oxidation state of that central atom, the more acidic the protons are to be in those oxyacids. The cation forms a stronger acid than the neutral molecule, and the neutral molecule forms a stronger acid than the anion. So if we're looking at hydronium, water, and the hydroxide, the hydronium atom is the strongest acid. It's got a positive charge. It's much easier to lose a proton than the water or the hydroxide. And the water is in the middle. It's easier for it to lose a proton than the negatively charged hydroxide. So the base has the opposite trend. So for ammonium, losing that proton is easier for ammonium than it is ammonia. And then losing the proton from ammonia is easier than the NH2 minus, because remember the NH2 minus has a -1 charge. It's going to be even harder to lose another H plus to form the NH2 minus. The acid strength is measured by the size of the equilibrium constant when the acid reacts with water. And the equilibrium constant is called the acid ionization constant, or the Ka. And the K still represents the equilibrium constant for the mass action equation, and it's still products over reactants. We're just indicating that it's an equilibrium constant for an acid by having the lowercase a next to the K. So you're just having that little a there to represent constant associated for an acid dissociating. And remember, the larger the Ka, the stronger the acid. So the larger the Ka, the more products that you have, because remember the Ka is still products over reactants. So we have the concentration of our acid and the concentration of our hydronium over the concentration of our reactants. And notice that water is a pure substance, so it doesn't show up in our Ka expression. So the larger this Ka is, the more products that we have, and the more products that we have means the more that the acid is dissociated. And the more it's dissociated, the stronger that acid is, because it produces more H+ in solution. So this is just a table that you'll find in your book to just give you examples of common weak acids, and it shows where the acidic hydrogen is on the structure, but it also gives you the equilibrium constants associated with those reactions. So if you need some of those values, you can find that in the table in your book. Again, this is just another table of different acids and their equilibrium constants associated with them. And remember, phosphoric acid is a triprotic acid. And we said that removing each hydrogen becomes more and more difficult, and those 3 hydrogens are removed one at a time. So notice that the first association constant, the acid equilibrium constant for removing the first proton, is 7.52 times 10 to the minus third. The equilibrium constant for removing the second ion is 6.2 times 10 to the minus 8. So this second number is a smaller number, which is showing that it's more difficult to remove the second proton compared to the first. And that third one is even more difficult to remove. So that's 10 raised to the negative 13th. So the smaller the K value, the more difficult it is to remove that proton. So that ends our series for video lecture 1 for chapter 15. So you'll find another recorded lecture for part 2 where we start to introduce pH as a measure of the strengths of an acids and bases. 2 hydrogens, that's the equilibrium